Hi, welcome to this video. Today we're going to talk about the Lempel Ziv algorithm. But first we should know why we need it, so let's have a quick look at some history. Even though information theory was created in the 1940s, it wasn't until the 1980s that data compression became of practical interest. As the internet took off, people began to share images and other data formats that are considerably large. During that time, bandwidth and storage were either limited, expensive, or both. This is where data compression jumps in as a key solution. Although Huffman coding was already created, it required a probabilistic model of the source. Unfortunately, in real life, source statistics are not always known. So, to overcome these practical limitations, we may use the Lempel Ziv algorithm, which is more efficient and simpler to implement. The Lempel Ziv algorithm is now the standard algorithm for file compression used in softwares like 7-Zip and others. So, let's have a look at how it works. First of all, you should keep in mind that the idea behind encoding in the Lempel Ziv algorithm is described as follows. The source data stream is parsed into segments that are the shortest redundancies not encountered previously. Consider the example of an input binary sequence specified as follows. So we're going to have this binary sequence of zeros and ones, and we're going to tokenize this sequence into a set of subsequences. Each subsequence will have a numerical position, which will be an index, and after that, each subsequence will have a numerical representation that we're going to talk about. And finally, we're going to have our binary encoded blocks, which is the main thing we want to get to. The encoding process begins at the left. The first bit seen is 0, and which is encountered for the first time, so it's gonna be our first subsequence, and it will have a position of 1. Moving to the next bit, which is in this case a 1, it's also encountered for the first time, so it's gonna be our second subsequence, with the position of 2. Moving on to the next bit, we get to a 0. Comparing with the bits that came before it, it has already been encountered, so we need to consider this bit and the bit that comes next to it. In this case, we also have another 0, so we end up with a sequence of 0, 0. Comparing with the previous bits, this is our first encounter of 0, 0, so we will add it to the list of subsequences and it will have a position of 3. In similar fashion, we may continue with the rest of the input stream. So moving on, we get to a 0, already encountered before, next to it a 1. So 0, 1, this is encountered for the first time, so we're going to add it to the subsequences, 0, 1, and it will have a position of 4. Similarly, we move to the next bit, which is 0. It's already mentioned, so we move to the next bit, which is 1. We have a 0, 1, which is already a subsequence with a position of 4. So we have to move to the third bit, so we obtain 0, 1, 1. This is the first encounter of 0, 1, 1, so we add it as a new subsequence, and it will have a position of 5. Carrying on, we get to a 1. It's already encountered. Moving to the next bit, we have a 1, 0. So it's the first encounter of 1, 0. We add it as a new subsequence with a position of 6. It's actually straightforward, and we have to carry on with the rest of the stream in the same manner. If we continue with the rest of the stream, we will obtain 3 new subsequences, 0, 1, 0, 1, 0, 0, and 1, 0, 1, which we will add. At this point, we will have finished gathering our subsequences and given each one of them a position. Now we will have to move to the next step of giving each subsequence a numerical representation. Now in the rest of the subsequences, the last bit of each subsequence is called the innovation symbol that I will underline in red, and the rest of the bits I will underline in green. Now you have to map every set of bits underlined in green to the numerical position of the subsequence it belongs to, which is very straightforward. For example, in the first one, I have a 0, which has the numerical position of 1, so I add a 1. In the next one, I have also a 0, which is a 1. In the next, I have 0, 1, which has a numerical position of 4. In the next one, I have 1, which has a position of 2. In the next, I have 0, 1, which also has a position of 4. In the next, I have 1, 0, which has a position of 6. And in the last one, I also have 1, 0, which also has a position of 6. Similarly, we do the same thing with the innovation symbol that is underlined in red. But in this case, it can only be 1 or 2, because it's a single bit, either 0 or 1. So in the first case, it's 1. Second case, it's 2, 2, 1, 1, 1, and 2. We arrive at the last step, getting the binary encoded blocks. For the first two subsequences 0 and 1, they will remain as they are. As for the rest, the first step is to copy the innovator symbol and also set it as the last bit. After that, we have to take the first digit of each numerical representation, which I will underline in blue, and convert them from decimal to binary. So the first digit we have is a 1, which is gonna be a 001. The second digit is also a 1, which will be the same. The third one is a 4, which will be converted to 100. Then we have a 2, which will be converted to 010. Then we have also a 4, which will be converted to 100. And then we have a 6, which will be converted to binary 110. And lastly, we also have a 6, which will be converted to 110. Finally, we have our encoded string. Notice that in this simple case, the encoding is actually a longer string than the source. This is because there was no obvious redundancy in the source. In practical implementations, where the strings may be millions of bits long, usually look at the last 32 kilobytes of processed symbols, and where probably a lot of redundancies occur. I hope this video helped you have a better understanding of the Lempel Ziv algorithm, and thank you for watching.